Imagine you just, walk up to someone on the street and you just ask them for the time.
Simple enough.
Right. But instead of glancing at their wrist and saying, it's 2 p.m., they stop, clear their throat, and just start explaining the entire history of horology to you.
Oh, no.
Yeah. They tell you about the invention of the mainspring in the 15th century. They, break down the mechanics of a quartz oscillator.
Yeah.
They even pivot into the physics of time dilation and relativity. And then, 20 agonizing minutes later, they finally look at you and say, oh, and it's 2 p.m.
Wow. They gave you the right answer.
Exactly. You got the right answer, but you are completely exhausted. And, you're already late for your meeting.
Right, because it's technically correct, but practically useless just because of the delivery. We value precision, obviously, but we also put a massive premium on efficiency.
Yes.
When getting the answer takes more energy than the answer is worth, well, the system is fundamentally broken.
And that tension, that exact tension between being correct and being concise is the entire engine of our deep dive today. So welcome in.
Glad to be here.
If you are listening to this, you are probably someone who loves grabbing high-value knowledge quickly, without getting bogged down by information overload.
Which is pretty ironic given our topic today.
It's the absolute irony, because today we are exploring how researchers are trying to teach generative AI not to overload us with too much information. We're pulling insights from Gen AI Foundation's podcast alongside a really fascinating state-of-the-art preprint paper.
Yeah, it's a great paper.
It's titled LACONIC. That stands for Length-Aware Constrained Reinforcement Learning for LLM, put together by just a powerhouse team of researchers from UCLA, Salesforce AI, National University of Singapore, and the University of Alberta.
And I got to say, this represents a major technical achievement in the field right now.
Really?
Oh, yeah. What we are really examining here is a massive leap forward in balancing pure brute force reasoning performance with actual computational efficiency. It's really about teaching these systems to self-edit.
Okay, let's unpack this. Because to really appreciate the fix, we need to look at this funny, honestly, strangely human-like flaw that modern AI has developed.
Right, the verbosity.
Yeah. We're looking at the underlying architecture of top-tier models today. Your GPTs, Geminis, DeepSeeks, Claudes. The industry has seen just unbelievable success using reinforcement learning to fine-tune them.
Yeah, RL is everywhere now.
We're talking about training a model by giving it a reward when it gets something right, like giving a dog a treat when it sits.
Exactly. It's reward-driven optimization, and it has been absolutely pivotal for refining advanced reasoning skills.
It really has.
It is why modern AI is suddenly incredible at complex math, generalization, coding. The model tries different logical paths, interacts with an environment, and then gets a positive signal when it arrives at the correct final answer.
Right, it gets the treat.
Exactly.
Mm-hmm.
But the mechanics of that reward system have, inadvertently created a monster.
A very wordy monster.
Yeah, because these models are rewarded for spelling out logical steps to arrive at the correct answer. Over time, the model figures out a cheat code.
What's the cheat code?
It realizes, hey, if I just keep generating text, if I give myself an endless scratchpad of tokens to work with, I increase my statistical chances of eventually stumbling upon the correct logic.
It's exactly like having a brilliant but exhausting coworker.
Yes.
You send them an email asking a simple yes or no question like, did we secure the new client? And they reply with a 12-page document.
Complete with footnotes.
Literally. They detail the history of the client relationship dating back to 2018, the psychological state of the room during the pitch, the weather that day, just to finally say yes, buried at the very bottom of page 12.
Right.
They are brilliant, they're correct, but they're completely draining your energy.
And in the context of large language models, that draining of energy is not just a fun metaphor. It is literal physical energy.
Yeah. Oh, wow. Yeah.
We have to look at why this verbosity matters practically.
Mm.
This isn't just, a minor annoyance for the user who has to scroll past a wall of text. Excessive length inflates both training time and inference time.
Which is money.
A lot of money. It puts massive pressure on GPU memory, which is the most constrained resource in the tech world right now.
Yeah.
Every single token the model generates requires complex matrix multiplications.
So it's not just thinking, it's calculating.
Exactly. So when an AI overthinks a basic math problem, it is actively wasting expensive compute resources, consuming measurable amounts of power, and degrading the user experience. You're sitting there waiting for it to finish a monologue that just didn't need to happen.
Wait, I gotta ask though. If the model is talking too much, why can't we just tell it to stop?
Yeah.
Like, just give it a penalty for every extra word. If the problem is too many tokens, just subtract a tiny fraction of its reward for every single token it spits out. That seems like the most obvious, easy fix in the world. Tax the output.
It seems highly intuitive. And honestly, that is exactly what the industry has tried to do up until this paper.
Oh, really?
Yeah. There are several prior methods that rely on what we call fixed heuristic reward shaping.
Okay.
You might see methods called L1, or efficient reasoning, or think prune, and they all operate on the exact premise you just described. They hard code a length penalty directly into the training process. They charge a tax for talking.
But I'm guessing, since we have a whole new paper about this, the simple tax idea doesn't actually work.
What's fascinating here is why that fails so spectacularly.
Okay, why?
When you hard code a fixed length penalty, you fundamentally misalign the training objective with the actual task you want the AI to do.
Misalign how?
Well, think about the underlying math the AI is trying to optimize. The true reward is getting the user's prompt right,
Right.
answering the question.
But by introducing a constant unyielding penalty for length, you create a surrogate objective.
A surrogate objective. Yeah. The model is now trying to solve a complex calculus problem and be as brief as possible simultaneously on every single prompt it ever faces.
Because it's a machine optimizing for a numerical score, so it's just going to look for the path of least resistance.
Exactly.
It might realize that the easiest way to avoid the length penalty isn't to be concise. It's to just stop talking completely. Like, even if it means getting the answer wrong, maybe losing the reward for accuracy is mathematically better than paying the massive tax for a long, correct explanation.
You nailed it. It leads to incredibly brittle models. Finding the exact right penalty amount requires endless hyperparameter tuning.
Sounds like a nightmare.
It is. If you make the penalty too high, the model's accuracy simply plummets because it cares more about being short than being right.
And if it's too low?
If you make the penalty too low, the model mathematically decides the tax is worth paying, ignores it, and just keeps rambling anyway. It is a rigid system trying to solve a dynamic problem.
Right, because not all problems are the same size.
Exactly. Math Olympiad problems naturally require far more tokens than simple arithmetic. A fixed penalty punishes the model for showing its work, even when showing its work is structurally necessary to solve the problem.
Here's where it gets really interesting, because the researchers behind this LACONIC paper looked at that rigid system and realized, hey, you cannot use a fixed penalty. You need something fluid.
Yes.
So they introduced an algorithm called LACONIC, which, again, stands for Length-Aware Constrained Policy Optimization. And the name is brilliant because LACONIC literally means expressing much in few words.
It's a great acronym.
Very clever. So how does it actually work?
At its core, LACONIC is a Primal-Dual Algorithm. It enforces a target token budget during training, but it does so without compromising the model's performance on the actual task.
Okay.
It maximizes the task reward subject to an average token budget constraint across a batch of prompts, rather than forcing a strict limit on every individual sequence.
Okay, let's bring this Primal-Dual concept into the real world for a second. Imagine a dynamic toll road.
Okay, I like this.
The city planners set a target. They only want, say, 1,500 cars on the road per hour to keep traffic flowing perfectly. That is our token budget, which the researchers call B.
Right.
Now, the city doesn't just slap a flat $5 toll on everyone 24/7. Instead, they use a dynamic toll multiplier.
Yes, and that system actively monitors the traffic. This represents the dual update part of the LACONIC algorithm.
Dual update. Okay.
If the average traffic, so the average length of the AI's responses across a whole training batch starts creeping over that 1,500 limit, the toll goes up.
Got it.
The algorithm recognizes that the model is generating too many tokens overall, so it makes it more mathematically expensive to generate long answers.
And we can take that analogy even further. Think about the GPS system in those cars. That's our AI model.
Sure.
If the toll is 0, the GPS routes you on the most natural, sprawling, scenic route because, well, there's absolutely no penalty. But the second that dynamic toll goes up, the GPS recalculates.
It absolutely does.
It starts actively seeking shortcuts, cutting out unnecessary detours, and finding the tightest possible route to save money.
And that recalculation, that is the primal update.
Ah, primal update.
Yeah. And the researchers implemented this using a really brilliant mechanism they call a clipped cost function.
Clipped cost. How does that math work?
Mathematically, they take the length of the response, subtract the budget, and divide it by the budget to get a percentage. But the genius part is the clipping.
Right.
If that resulting number is negative, meaning your response was under the budget, They just zeroed it out.
Oh, so translating that into plain English, if your response length is under the budget, your cost is literally zero. There is absolutely no penalty at all.
Exactly. Unlike previous heuristic methods that slap a tax on every single word no matter what, the clip cost ensures there is no artificial pressure to shorten a response that is already concise enough.
That makes so much sense.
The model can focus entirely on accuracy, but the moment it goes over the budget, that cost kicks in, scaled by the dynamic multiplier we just discussed.
Wait, I want to push back on this batch average idea for a second.
Sure.
If the algorithm looks at an average across a whole batch of prompts, doesn't that create a weird vulnerability?
How so?
Let's say a batch has 10 prompts. The first 5 happen to be wildly complex physics problems that legitimately require like 2,000 token answers.
Okay.
The model's average skyrockets. Isn't it going to abruptly panic, crank up the dynamic toll, and severely punish the 6th prompt, forcing the AI to give a wrong, stunted answer just to drag the average back down?
That is a great point, and it's exactly the kind of friction you would expect in a naive implementation. However, this is why the dynamic multiplier updates iteratively over massive training steps rather than wildly oscillating prompt by prompt.
I see.
The training batches in modern RL are enormous, often thousands of sequences. Law of large numbers dictates that the natural blend of complex and simple problems smooths out.
So it's not looking at just 10 prompts.
Right. The algorithm isn't panicking over a single physics problem. It's looking at the macro behavior of the model.
Okay.
If the model gets a really hard calculus problem, it can absolutely use 3,000 tokens to solve it, provided it balances that out by answering simple arithmetic questions in 100 tokens, keeping the overall macro average under the budget.
It basically gives the model room to breathe.
Precisely.
So the theory is beautiful, but, we all know how AI research goes.
Yeah, we do.
A paper can have elegant, pristine math that completely falls apart the second you run it on a real GPU. The logic makes sense on a whiteboard, but does it actually hold up under the pressure of real data?
It absolutely holds up. The benchmark results in this paper are astounding.
Let's hear them.
So the researchers tested LACONIC on 2 primary reasoning models, DeepScaler 1.5b and DeepSeek 1.5b.
Oh, okay.
They ran them through the gauntlet of 4 notoriously tough math benchmarks: AME 2024, Math, Minerva, and Olympiad bench. And they evaluated them using pass at 1 accuracy.
So that means the percentage of questions where the model's very first generated response is correct, right? No second tries.
Exactly. 1 shot.
The numbers they pulled are wild. Like, let's look at the DeepScaler model. When they applied LACONIC, it essentially preserved the exact same pass at 1 accuracy as the baseline model. It didn't get dumber,
Yep.
but it used 52% fewer tokens to do it. Over half the bloat. Just gone.
And the DeepSeek 1.5b results were even more pronounced. LACONIC reduced the average response length by a staggering 71%.
71%.
Yeah. It went from averaging around 9,900 tokens down to roughly 2,900 tokens. And it achieved that massive reduction with a negligible 2.08-point drop in overall accuracy.
That's incredible.
It really is. Because when the other baseline methods, like efficient reasoning or think-prune, tried to force the models to be that short, their accuracy simply tanked.
Yeah.
LACONIC was the only method that maintained the underlying brilliance while curing the exhaustion.
There is a specific case study buried in the paper that brings this to life perfectly, I think.
Oh, the Aya problem.
Yes. It's a word problem about a girl named Aya walking to a coffee shop. It says Aya walks 9 kilometers, stops at a coffee shop for a certain amount of time. Let's call it minutes. If she walks at speed says, the whole trip takes 4 hours. If she walks slightly faster, at s plus 2 kilometers per hour, it takes 2 hours and 24 minutes.
Classic rate, time, and distance problem.
Right. And the question asks, how long does it take if she walks at an intermediate speed of s plus 0.5 kilometers per hour?
So to solve that, it requires setting up a system of equations, isolating a variable, solving a quadratic equation to find her original speed, and then substituting that back in to calculate the final time.
Okay, so they fed this prompt to the standard model tuned with normal reinforcement learning, and it solved it. The correct answer is 204 minutes. But to get there, the standard model took a rambling 1,763 tokens. When you read the actual thinking trace provided in the paper, it's doing exactly what you described earlier.
Exploring blind alleys.
Totally. It converts hours to minutes, then halfway through decides to convert back to hours. It writes out complex polynomials, expands them completely, realizes it didn't need to do that, and then cancels the terms back out. It's spinning its wheels, generating noise.
It is a textbook example of the overthinking behavior induced by unconstrained reward systems. The model is exploring blind alleys because, well, it has no incentive not to.
Then they give the exact same problem to the model trained with LACONIC, and it solves it in 855 tokens, less than half the time.
Amazing.
The output is surgical. It identifies the two scenarios immediately, sets up the two equations, subtracts one from the other to instantly eliminate the time variable, solves the quadratic equation for speed, plugs it back in, gets 204. Done.
It's beautiful.
It is like watching a master craftsman work versus an amateur fumbling with tools.
And, the benefits extend far beyond high-level mathematics, too. The researchers tested LACONIC out of domain as well.
Meaning on non-math stuff.
Exactly. They evaluated it on general knowledge and complex logic tests like GPQA, the LSAT, and MMLU.
Yeah.
LACONIC maintained the accuracy of the base model while generating 44% fewer tokens.
Oh, wow. So it generalizes.
Yeah, it didn't just memorize a trick to do math faster.
Yeah.
The model fundamentally learned a general principle of conciseness.
Which brings us right back to the real-world impact. We talked earlier about GPU pressure.
Yes, the compute cost.
The paper points out that because the LACONIC train model is generating fewer tokens during the training process itself, the actual wall clock time required to train the model is 19% faster. Plus, it uses 22% less GPU memory.
That is massive. Anyone familiar with the economics of modern AI knows that renting high-end GPU clusters costs a fortune. Reducing memory requirements by 22% and training time by 19% translates to millions of dollars saved for AI labs.
Million?
Yes, it lowers the barrier to entry, making advanced reasoning models significantly more sustainable to train and far cheaper to deploy to end users like you.
So what does this all mean? I mean, we know LACONIC works because of this highly specific Primal-Dual clipped cost setup.
Right.
But what happens when developers read the headline of this paper, decide they want the efficiency, but take the lazy route? What happens if they skip the dynamic budget and just use a standard linear cost where every single token is penalized?
Well, this raises an important question, and the researchers actually mapped out that exact scenario in an ablation analysis.
An ablation study?
Yeah, an ablation study is where you strip away core components of an algorithm to see if they are actually necessary.
Okay, so they stripped it down.
They did. When they stripped away the clipped cost and applied a basic linear penalty to a model called QuenMath 1.5b, the results were catastrophic. The model suffered a sharp length collapse.
Length collapse? That sounds like a structural failure.
It is a total breakdown of the model's utility.
Huh.
Within the first few hundred training steps, the average response length plummeted to below 10 tokens.
10 tokens? I mean, you can barely say hello in 10 tokens, let alone solve a quadratic equation.
Precisely. And consequently, the model's accuracy fell off a cliff, dropping from roughly 40% down to 8%.
Ouch.
Yeah. We have to look at the mechanism of this failure. Why does a linear penalty cause length collapse? Because when every single word costs points, the model evaluates the math. Even if I get the right answer, the 500 words it takes to mathematically prove it will cost me more penalty points than the positive reward I get for being correct. Oh, so the most mathematically rational move for the AI is to just shut up and fail.
Exactly. It chooses to fail silently rather than succeed verbosely, because failing silently incurs a smaller total penalty. The training dynamics become utterly unstable.
Wow.
This is the definitive proof that you cannot just slap a linear tax on the output. The magic of LACONIC is entirely reliant on the clipped cost.
Right, allowing the model to operate completely penalty-free as long as it's under the macro budget.
Exactly, and only applying pressure when the batch average exceeds the limit.
It's the difference between a punishing boss who docks your pay every time you speak in a meeting and a good manager who just taps their watch when the overall meeting is running long.
I love that analogy.
The first one makes everyone terrified to share good ideas. The second one just keeps the team focused and on track. Exactly. LACONIC provides robust, reliable length control without forcing engineers to constantly tweak brittle hyperparameters for every new dataset.
So wrapping this up for you listening right now, whether you are actively building AI applications, investing in the space, or just observing the incredible pace of this technology, efficiency is undeniably the next major frontier.
It is the frontier, yes.
We have spent the last few years just trying to make these massive models smart. Now we have to make them usable.
As token generation costs and data center energy usage become genuine global macroeconomic concerns, algorithms like LACONIC are what will bridge the gap between theoretical capability and sustainable deployment.
Absolutely.
It definitively proves that an AI does not have to be bloated to be brilliant.
It is a massive paradigm shift. We are moving away from models that just dump raw information and hope the answer is in there somewhere, toward models that actively curate their own thoughts.
Yes.
We don't just want the smartest watchmaker in the room. We want the smartest watchmaker who also knows how to read the room and just give us the time.
It's a critical evolution in artificial reasoning.
And I want to leave you with one final mind-bending thought to mull over.
Okay.
We've seen today that LACONIC teaches an AI to constrain its thinking to a strict budget without losing accuracy. It effectively forces the model to hunt for the most direct path to a solution.
Right.
But what happens as we deploy this on the most advanced supermodels in the world and we push that budget tighter and tighter? Could this constraint eventually force an AI to discover entirely new, ultra-efficient mathematical shortcuts and logic paths that human mathematicians haven't even thought of yet?
That is fascinating.
Sometimes when you restrict the space, you don't just get brevity, you force a breakthrough. Just something to think about. Till next time.